Welcome to the Deep Dive. You're here because you want the core knowledge, the aha moments, without getting bogged down in endless details.
Exactly. We get it.
And that's what we deliver.
So today, we're diving into something pretty significant that you flagged. Google DeepMind's Gemma 3.
Right. Not just another incremental update, is it?
Now, seems like a real step forward in their open language model family.
And our source is the Gemma 3 technical report itself. Quite dense.
It is. Our mission, then, is to pull out the really key stuff. What's new, what's exciting, and how does it actually stack up against what came before?
Okay, let's get into it. First, big headline. Multimodality. Gemma 3 can see now.
Well, sort of. The 4B, 12B, and 27B models, yeah, they can now understand visual input.
Wow.
They've integrated it with a tailored version of their SIGLIP vision encoder.
Okay, so it's not just text anymore.
Exactly. It's processing images alongside text. A big leap.
So how does a model build for language, even like process an image?
That's the clever bit. It treats the image as a sequence of soft tokens.
Soft tokens.
Yeah, think of them as like numerical summaries of what's in the image, generated by that SIGLIP encoder.
Okay, summaries. But images can be complex.
Right. So for efficiency, especially during inference, when you're actually using the model, these visual summaries get condensed down.
Condensed how much?
Into just 256 vectors, a fixed size.
256, that sounds quite small for an image.
It is, but it's designed to keep the computational costs down. Makes processing images practical, not a huge resource drain.
So the insight is, vision's here, but it's built to be efficient. Makes sense.
Exactly.
But, real-world images aren't all neat squares. They're all different shapes, sizes, resolutions.
Good point. And they have a solution for that called pan and scan. PNS for short.
Pan and scan. Like a camera.
Sort of, yeah.
Yeah.
They took inspiration from another model, Elavi.
Okay.
Basically, if Gemma 3 gets an image that's, say, a weird aspect ratio or really high res.
Which happens all the time.
Right. It can break that image down into smaller, non-overlapping chunks or crops.
Segmentation.
Exactly. And then each of those crops gets resized to a standard format. The vision encoder expects 896 by 896 pixels.
So it takes little snapshots across the image. Does that add a lot of processing time?
Well, it's an inference time optimization. It only kicks in when needed.
Oh, okay.
And the report actually mentions you can disable it if speed is absolutely critical and you don't need that flexible handling.
So optional optimization. What really stands out to you about this vision capability?
For me, it's that practicality focus again.
Yeah.
Condensing the data, the PNS, for weird formats. It shows they're thinking about real-world usability, not just ticking the vision box.
Yeah, agreed. Making it workable.
Yeah.
Okay, next big jump. Long context.
Oh, yeah, this is huge.
Gemma 3 boasts 128,000 token context window. That's massive, right?
Okay.
Except for the smallest 1B model, which still gets 32K.
It's a very significant increase. 128K tokens, that's like a short book's worth of text it can hold in its working memory at once.
Wow, so it can follow conversations or analyze documents that are much, much longer.
Exactly. Maintain coherence, track relationships over extended text. But there's a catch.
Always a catch. What is it?
The technical report highlights the challenge, the KV cache memory requirements.
Right, the KV cache.
Yeah.
That's the short-term memory for process words, yeah.
Precisely. And with these super long sequences, that cache can just, well, explode. It needs tons of memory during inference.
So how do they solve the memory explosion?
With a pretty neat architectural trick. They alternate different types of attention layers.
Okay.
They interleave 5 local self-attention layers, which only look at a small nearby window of 1024 tokens between each global self-attention layer.
And the global ones.
Those are the ones that can see the entire 128K token context.
So not every layer needs to look at everything all the time.
Exactly. The local layers handle nearby context efficiently. The global layers handle the long-range dependencies, but less frequently.
That sounds much more memory-friendly.
It is. It significantly reduces the KV cache burden. So the insight here isn't just longer context, it's longer context made practical through clever architecture.
Smart. Do they need any other tweaks for that?
Yep. They also had to adjust something called the ROPE base frequency.
ROPE, rotary position embeddings. Helps it know where words are.
That's the one. For those global attention layers looking at the full 128K, they crank the base frequency way up from 10K to 1 million.
A big jump. Why?
Could help the model accurately understand the position of words over such vast distances. Without that, things can get muddled in very long sequences.
Okay, so local global attention plus tweaked ROPE makes 128K feasible. That could really change things.
Definitely opens up new applications.
All right, moving on. Multilinguality. Gemma 3 is better with other languages.
Seems so, yes. They explicitly revisited the training data mix
Oh.
by adding more monolingual data, just text in one language, and also more parallel data, which is text paired with its translation, and critically, across more languages than before.
So less English-centric training.
That seems to be the goal. They also mentioned using a strategy, inspired by some previous research, to handle imbalances.
Imbalances, like way more data available for one language than another.
Exactly. To try and make the model perform more consistently across different languages, even those with less data.
And the tokenizer. That's important too, right? For breaking down words.
Crucial. They're using the same tokenizer as Gemini 2.0. It has a larger vocabulary, 262,000 entries, and it's specifically designed to be more balanced for non-English languages. Doesn't chop them up as inefficiently.
Makes sense. More languages in, better tokenizer.
Yeah.
Should lead to better multilingual skills. Okay, let's talk performance. Did all these changes pay off?
According to the report, yes. Overall, Gemma 3 either matches or beats previous Gemma versions.
And specific improvements.
They highlight a novel post-training recipe. This seems to have really boosted math, chat abilities, following instructions, and, as we just discussed, multilinguality.
Interesting. So the fine-tuning stage was key. Any standout comparisons?
Yeah, this is quite impressive. The Gemma 3 4B IT model, the 4 billion parameter one tuned for instructions, it's apparently competitive with the previous generation's much larger Gemma 2 27B IT.
Wow, a 4B keeping up with a 27B, that's a big efficiency gain.
It really is. And the new Gemma 3 27B IT, it's holding its own against Gemini 1.5 Pro on several benchmarks. Table 6 in the report lays out the numbers.
Comparable to Gemini 1.5 Pro, that's a serious claim for an open model.
It is, and it answers that how does it stack up question pretty clearly. Very well, it seems.
What about human evaluations? Like the chatbot arena?
Yes, the LMSYS chatbot arena. Table 5 has some preliminary results. The Gemma 3 27B IT model got an ELO score of 1338.
ELO, like in chess rankings, higher is better.
Exactly, and 1338 puts it among the top open models, significantly higher than Gemma 2.
Better than which other models?
Well, notably, the report claims it ranks above other big open models like DeepSeek V3 and even Llama 3 405.
The Llama 3 405B, that model is huge.
Vastly larger, yes. So, Gemma 327B seems to be punching well above its weight in these human preference scores.
That's really striking. Smaller model, top-tier performance in human evils. Okay, the report also dives into ablation studies, right? Taking things apart to see what matters.
Yes, and those offer some useful insights into why it performs well.
Like what?
Well, remember the local versus global attention layers for long context?
Yeah, the 5 local to 1 global ratio.
They tested other ratios, like even 7 local layers to 1 global layer.
And performance tank?
Surprisingly, no. The impact on perplexity, how well it predicts the next word, was minimal. Figures 3 and 4 show this.
So they could potentially make it even more memory efficient with more local layers.
Potentially, yeah. They also found the size of the sliding window for those local layers, the 1024 tokens. It could likely be made smaller without much performance loss either.
Interesting. More efficiency headroom.
And this ties directly back to the KV cache memory we talked about.
Right.
Figures 5 and 6 in the report confirm that their chosen 5.1 ratio with the 1024 window does significantly cut down memory usage compared to a purely global attention model.
So the architecture choices are definitely validated by these tests. What else did the ablations show?
They looked at how they achieved the 128K context. They confirmed their strategy worked well, pre-trained mostly on shorter sequences like 32K tokens, and then towards the end, stretched it out to 128K using that row P rescaling technique. Figure 7 shows this scaling works.
Efficient training too. Start short, scale up later.
Exactly. And another quite nuanced finding, this is in Figure 8, was about knowledge distillation.
Learning from a teacher model.
Right. They found that if you're training for a shorter time, a smaller teacher model can actually be better.
Really? Not the biggest, smartest teacher.
Not always, apparently. But for longer training horizons, then yes, the larger teacher model became more effective. It depends on the training duration.
Huh. That's counterintuitive. So the best teacher isn't always the biggest.
Seems that way. On the vision side, Table 7 confirms something maybe more expected. Higher resolution vision encoders lead to better visual understanding performance.
Okay, better eyes, better sight. Makes sense.
And Table 8 really highlighted the benefit of that pan and scan method.
The PNS cropping thing.
Yeah, it showed significant gains on visual question answering tasks, especially for images containing text or those with unusual aspect ratios.
So PNS isn't just a theoretical fix, it really helps in practice for diverse images. Got it. Let's talk about the training nuts and bolts. Knowledge distillation was key, you said.
Yes, all Gemma 3 models leverage knowledge distillation, learning from larger, presumably more capable, teacher models.
And the sheer amount of data.
Masses. They mention a much larger token budget compared to Gemma 2. The example given is 14 trillion tokens for the 27B model pre-training.
14 trillion. It's hard to even conceptualize that amount of text.
It's astronomical. And of course, they applied various filtering techniques to clean that data, trying to reduce unwanted or unsafe content, PII, and so on.
Quality control on the input.
Right. They also use quantization-aware training, QAT.
Yeah.
It lets them produce quantized versions of the model's compressed versions that need much less memory to run. Table 3 shows the smaller memory footprints, very useful for deployment.
Right, making them runnable on less powerful hardware and the hardware they use for training.
Top-end stuff. Google's TPUs, specifically TPU v4, TPU v5e, and TPU v5p. Table 2 lists the infrastructure.
Okay, so massive data, distillation, quantization, powerful hardware. What about the instruction tuning, the IT models?
That's a whole separate, crucial stage after pre-training.
Right, to make them helpful and follow instructions.
Exactly. They used an improved knowledge distillation process again, learning from a large instruction-tuned teacher. Then, crucially, reinforcement learning fine-tuning.
RL, like RLHF.
Sort of, yeah. They used techniques called bond, warm, and warp, along with various reward models targeting different capabilities, helpfulness, reasoning, coding, math, instruction following, even multilinguality.
A complex tuning process.
Very. And Table 4 reminds us about the importance of specific tokens like BOS for beginning of sentence and end off turn for structuring the conversation properly for these IT models.
Little details,
Right.
but critical for the model to understand the flow. Okay, a big concern always. Memorization and privacy.
Yeah.
How does Gemma 3 fare?
They seem to have put effort into measuring this. They looked for instances where the model's output matched text from the training data using both exact and approximate matching.
And the finding?
Figure 9 in the report shows a key result. Gemma 3 models apparently memorize long-form text at a much lower rate than their previous models.
Oh, that's definitely good news. Less regurgitation.
It's a positive trend, yeah.
And for privacy specifically.
Did they check for personal info?
Yes. They use Google Cloud's sensitive data protection service on the outputs flagged as potential memorization. The report states they found no personal information in those outputs for any of the Gemma 3 models, basically below their detection limits.
So the filtering and training seem pretty effective at minimizing that specific privacy risk. That's reassuring. It suggests progress in that area, yes.
Finally, the report talks a lot about responsibility, safety, security.
Absolutely. This is clearly a major pillar for them. They talk about building on their experience from Gemma 1, Gemma 2, and the Gemini models.
Enhanced safety processes.
Yes, integrated throughout development. They have specific safety policies to prevent generating harmful content, hate speech, harassment, illegal acts, etc.
Standard categories, but important.
And they apply safety filters to the pre-training data itself, plus use supervised fine-tuning, SFT, and RLHF during the instruction tuning phase, specifically to steer the models away from unsafe outputs.
So safety built in multiple stages.
That's the idea. Their internal safety evaluations apparently showed a significantly low violation rate against their policies.
Okay. Any other specific safety checks?
They mention evaluating knowledge in sensitive domains like CBRN, chemical, biological, radiological, nuclear.
Yeah.
They found Gemma 3 models have low knowledge in those areas, which is generally considered a good thing from a safety perspective. Reduces misuse potential.
Right. Don't want models readily explaining dangerous procedures.
Exactly. Their overall stance is responsible open model development sharing when they judge the benefits outweigh the risks.
Okay, so wrapping this up for our listeners, Gemma 3 feels like a pretty substantial leap, doesn't it?
I think so. You've got vision capabilities added in. That massive long context window made practical.
Yeah, the 128K.
Improved multilinguality and really impressive performance, especially considering the model sizes.
Right, punching above its weight, particularly that 27B model, and all built with efficiency and safety. seemingly front of mind.
Yeah, those architectural choices for memory, the quantization, the safety filtering,
Ah.
it seems quite deliberate.
So the potential impact. These advancements could really unlock new ways of using these models, couldn't they?
Absolutely. Think about AI assistants that can understand charts in a document you upload, or coding helpers that can grasp the entire context of a large project, or chatbots that maintain much longer, richer conversations.
Yeah, the possibilities expand quite a bit. Which leads to maybe a final thought for our listeners.
Go on.
With models like Gemma 3 getting so much more capable and also more accessible as open models, what new possibilities do you see opening up?
Hmm.
And maybe just as importantly, what ethical considerations or challenges become even more critical as these powerful tools spread?
That's a deep question. Definitely something to chew on.
Food for thought. And of course, if you want every last detail, the Gemma 3 technical report is out there.
Highly recommended for the technically inclined.
Indeed. Thanks for taking this deep dive with us today.